Okay. Section 8.3, which is our last section of chapter 8, and this involves finding the inverses of our trigonometric functions. So we'll be able to see what that looks like both from a graphical standpoint and then utilizing our inverses from a technical standpoint as well. So what are our learning objectives for today? We're going to be able to understand our inverse sine, cosine, and tangent functions. We'll find our exact value of these expressions, and then we'll also find exact values of our composite functions with our inverse trig. So understanding and using the inverse sine, cosine, and tangent functions. At this point in the curriculum, we have a very good understanding of inverse functions. The biggest thing, if you don't already know this at this point, is knowing that you can only find the inverse of a function if it's one-to-one. And if it's not one-to-one, what we can do is we can manipulate the function by restricting its domain so that it is one-to-one. And the most common visual example of this is if we looked at just our quadratic function x squared, we know that this function is not one-to-one because it fails what test? Yeah, it fails our horizontal line test. So not one-to-one because fails our HLT, our horizontal line test. But if we restrict our domain to 0 up to infinity, now we're looking at part of this parabola, and now is this a one-to-one function? Yeah, so now it's one-to-one, which means we can find our inverse. And when we do, we end up getting our inverse of this function is just simply our square root of x. Positive square root of x. And visually, what does that look like? That just looks like this. Right? The reflection across the origin. Or I should say reflection across y equals x. Right? Definition of inverse, swap out your x's and your y's. So now bringing this knowledge into our trigonometric world, it's the same exact concept. When we're dealing with sinusoidal waves, right, that's gonna fail the horizontal line test everywhere, which is why it's so important to restrict our domain. So let's first look at how are we going to restrict our domain when we're dealing with our function sine of x. So this is our f of x is equal to sine of x. And we want to pick some good bounds that represents our function well, but then also passes the criteria of it is one-to-one, so it passes our horizontal line test. So technically, if we did a full period, a full cycle, which would be from 0 to 2 pi, would that be a one-to-one function? No, because it would fail our horizontal line test. So instead, we're going to restrict the domain from negative pi over 2 to pi over 2 because is this function one-to-one? Yeah, it passes our HLT everywhere. So with finding the inverse of sine functions, our domain is restricted to negative pi over 2 to pi over 2. And you'll notice as we go through our three famous trig functions, our domains are going to be restricted at different points depending on what function we're talking about. If we're talking about sine, it's negative pi over 2 to pi over 2. Cosine, we'll look at it in a moment. That's actually going to end up starting at 0. And then tangent, we'll look at that one in a moment as well. So if we specifically have this function restricted on this domain, then we can find the inverse of it. Now let's take a look at restricting our cosine function. In a moment. I think that's on, yeah, the next slide. Now let's look at finding the inverse of our sine function on that restricted domain. And so what do we do whenever we find the inverse of functions? Well, first we have to make sure it's one-to-one, and we did, right? It's restricted on negative pi over 2 to pi over 2. And then we apply our inverse rules. We swap out our x and y, and we solve for our new y and put it into proper inverse function notation. AKA, we reflect across our line y equals x because our x and y values are switching. And so our original function is what we have in red over here. And so when we do that reflection over our line y equals x, we get our nice visual of our inverse sine function, which is in blue. And then another major property to really know, it will make this section a lot more bearable, is when you're looking at your original function, and I'll maybe write this down on the side in a moment, but when you look at your original function and you calculate its domain, the inverse of that original function, that domain is actually the range of the inverse. So technically, if you know your original and you know your inverse, and you know your domain of your original and you know your domain of your inverse, then you can find the ranges of those corresponding functions very easily. You don't have to do any calculations. You just take this domain, put it in the range of the inverse. Take the inverse domain, put it in the range of your original, and then you have all of your domains and ranges calculated. So we'll utilize that strategy a few times during this lesson. So now let's maybe just write that down really quickly. So note our domain of f of x is the same as our range of f inverse x. And then we can also write, okay, well then the domain of f inverse x equals our range of f of x. And then the last thing that I want to mention on this slide is the comparison. So now that we're able to have that domain restricted to negative pi over 2 to pi over 2, then we can indeed find the inverse. So our inverse sine of x is equal to y is true when our sine of y is equal to x. And again, this is just applying our inverse to this and getting your output to be sine y equals x. I'll maybe just show it off to the side here, but this will erase in a moment. So if we take sine of both sides, then these cancel out and we get x is equal to sine y, which is what we have over here. Another way to state inverse sine function is just arc sine, and you'll see that a lot on your calculator. I think on your calculator they usually do sine inverse, but arc sine does pop up every now and then. So know that they're just synonyms of one another. And then up here, I know that we put the note, but our inverse sine function has a domain of -1 to 1, because again, that's our range for our regular sine function. And then the range of our inverse, we chose that to be restricted from -π/2 to π/2. Okay, now let's move on to cosine, which has different restrictions for our domain. So this is our visual of our cosine function, and we are going to restrict its domain from 0 to pi so that it indeed passes our horizontal line test now to make it 1 to 1. And so now we are able to find the inverse of our cosine of x. And so now keep in mind, this is the restricted domain on the original function, which means our inverse of cosine, this is going to be our range, right? So first, from the visual perspective, it's once again our reflection across our line y equals x. And again, our line y equals x is not the same as our reflection across our origin. So you just have to keep that in mind. It's when your x's and y values are just flipping. And then let's look at our domain and range. So our range is now that 0 to pi. And then our domain, well, what is our range for our function cosine of x? Our absolute minimum is -1 and our absolute max is 1. So we can write that down here. Range of cosine of x is from -1 to 1, which gives us our domain of our cosine inverse of x. And that's where we have our domain, -1 to 1. So we get our definition to be as follows: cosine inverse of x equals y, if and only if our cosine of y is equal to x. And we're done. Our original function is once again in red. Our inverse cosine is in blue. Are there any questions at all? No. Okay. So last but not least, now let's look at our tangent function and look at the restrictions we want to make here. And so recall from yesterday, our tangent function has vertical asymptotes at our intervals of pi/2. And so I should say, let's hone in on maybe this first one here, our negative pi over 2 to pi over 2. And so every pi gives you our period for our tangent of x. And between these yellow lines here, is this a good representation of passing our horizontal line test? Yeah. So between these yellow lines, we have indeed a one-to-one function, which means when we're looking to find our inverse tan function, our original function is going to be restricted on the domain of negative pi over 2 to pi over 2. And I'll once again write off to the side. All right, so a domain of f of x is restricted to negative pi over 2 to pi over 2. And there are no hard brackets because these are our vertical asymptotes, so our points are never going to hit at negative pi over 2 or pi over 2. But this is equal to our range of our inverse function. So inverse tan. Okay. Any questions at all? Another thing to just be mindful of, especially when you're just graphing tan functions, is that your x-intercepts hit at multiples of pi. All right. So now our inverse tan function, we already know what our new range is. Our new range is restricted at our negative pi over 2 to pi over 2. And then our domain shooting up, right? What's our range of our original tan function? It's all real numbers. We have no restrictions for our y values in both the positive and negative direction. So we get our range to be, and again, range of f of x is negative infinity to positive infinity. Which means that is our domain of our inverse. I'll put it as all real numbers too, which is what we have over here. Domain of inverse, all real numbers. Range of inverse, negative pi over 2 to pi over 2. Graphically, what does this look like? Our red is our original function, and then our blue is that reflection over our line y equals x. And we're done. Notice with our inverse tan function, now we're going to end up having horizontal asymptotes, whereas with the original, we had the vertical asymptotes between negative pi over 2 and pi over 2. Okay. And so our inverse tan of x is equal to y if and only if our tan of y equals x. Right, so what have we concluded over these past 6 slides? Our restricted domain for our sine x functions is from negative pi over 2 to pi over 2. For cosine, we restrict it from 0 to pi. And for tan, we also restrict it from negative pi over 2 to pi over 2. The difference, though, is you're not including the lower and upper bounds for tan because those are where the asymptotes take place. But with sine, we are including those boundary points. Right. Now we're finally on to our first example, which is more of a technical example, kind of just understanding our inverses of functions. We have sine of pi over 6 is equal to 1/2, and we want to write a relation involving the inverse sine. So first, let's just try and understand this. What does this mean? Sine of pi over 6 in terms of degrees is just 30 degrees. So sine at 30 degrees gives us that famous calculation of 1/2. But now let's apply our sine inverse. So we're going to take our inverse sine of both sides. And now we're looking at, okay, pi over 6 is equal to inverse sine of 1/2. Which kind of looks a little bit more confusing. But this is just essentially telling us, okay, sine of what angle gives us 1/2? Sine of pi over 6, sine of 30 degrees gives us that value of 1/2, which is inside our inverse function. And so that's it. We just wanted to write the relation involving that inverse sine. Second objective will be now utilizing that inverse sine function to do a lot more calculations. So maybe I'll have a student read this. Anyone? I'll highlight it in green. Ariana, go for it.
Now that we can identify inverse functions, we will learn to evaluate them. For most values in their domains, we must evaluate the inverse trigonometric functions by using a calculator, interpolating from a table, or using some other numerical technique. Just as we did the original trigonometric functions, we can give exact values for the inverse functions when we're using special ideas.
Good, thanks. So yeah, we're still utilizing our 0, 30, 45, 60, and 90 degree angles. So let's practice. And we're going to be using our knowledge of odd and even functions too. Odd in this case, because all sine-related functions are odd. So kind of just did this one. But sine inverse 1/2, this is just saying, okay, sine of what angle theta gives us 1/2? What's our theta here? In radians, it's pi over, yeah, pi over 6. And then in terms of degrees, that's just the same as 30 degrees. So either of these answers would work. Part B, we have inverse sine of negative 1/2. Well, this is just the same as negative sine inverse of 1/2 because sine is an odd function. And we just solved sine inverse of 1/2. That just gives us pi over 6. We just need a negative in front. So negative pi over 6 is our answer, or negative 30 degrees. And then this last one, there's a typo here. It should be square root of 3. And so again, we're asking ourselves, sine of what angle gives us the square root of 3 over 2? So what's our theta equal to? In radians, we get pi over 3. In degrees, that is 60 degrees. Which is why knowing that unit circle, knowing that table, is really important. It makes answering these questions, again, much more efficient. Yeah. Are you talking about like in terms of coterminal angles?
Like if for example A, the answer is 30 degrees, but there's more sine equals 1/2.
Yeah, so yeah, coterminal angles, yeah. Because if you plugged into your calculator sine of 390 degrees, that would also give you 1/2. Yeah. Usually when they say find each value, they'll put more of a restriction to it. They'll be like, find each value between 0 and 180 degrees. And then that's where there's only that one solution, known as like our base solution. But yeah, there's an infinite number of answers for these because a circle just goes on forever. So you can do any coterminal angle of 30, any coterminal angle of negative 30, or any coterminal of 60. Now let's look at it from the cosine perspective. So we'll do these a little faster pace. Cosine of what gives you negative square root of 3, or sorry, cosine of what just gives you positive square root of 3 over 2. We know sine of 60 gives you square root of 3 over 2, then cosine of, or they're opposites of one another, 30, right? Cosine of 30 gives you that square root of 3 over 2. So 30 degrees, or what's 30 in terms of radians? Pi over. Yep. What about part B? Cosine of what angle gives you 0? Yeah. Yes.
So the inverse is the same as,
Inverse is the same. Whenever you see, for example, cosine inverse of square root of 3 over 2 is equal to x, that square root of 3 over 2, actually, why don't we say is equal to theta? That's another way of just stating cosine of theta is equal to x. And that's just by our definition of cosine inverse of x is equal to y implies that our cosine of y is equal to x by our definition of inverse. So that's what we're doing. We're doing that whole manipulation. Essentially, it's just whenever you see the inverse, just treat this as your solution and figure out, okay, well, cosine of what angle will give me that solution? Yeah. And so yeah, cosine of what angle will give me this solution? About your unit circle. Where is your cosine, your x coordinate? When that's 0, what angle are we at? Pi over. Here, I'll show it to you visually. All right, we're looking at our unit circle. I'll plot in our major points. This is our coordinate point 1, 0. This is our coordinate point 0, 1. This is our coordinate point -1, 0. And this is our coordinate point 0, -1. And then in terms of angles, we have 0 degrees, we have 90 degrees, we have 180 degrees, 270, and then 360. And then remember our polar coordinates, our x comma y is the same as our cosine of our angle, comma our sine of our angle. So if we're looking at cosine of the angle, we're just looking at where is our x coordinate point 0. At 90 degrees and 270. If we were looking between 0 and 180, we would just choose 90. But that goes back to what Adam was saying about coterminal angles. So we have theta is equal to 90 degrees, also known as pi over 2. Technically, 270 isn't coterminal because coterminal is every 360 degrees, multiples of 360, or from radians every 2 pi. So here you could actually write those two solutions, 90 and 270. Adam, you had a question? You're going to ask that? Okay. Put this down here. Create some more space to write 270. So, and 270 degrees, which, what's that conversion in terms of radians? Good. Yes. And then last but not least, we have cosine inverse of negative pi over, or -1/2. Cosine functions are what, even or odd? The only even types of functions are cosine related. So because this is even, this is the same as just cosine inverse of +1/2. So essentially we're looking at, okay, cosine of what angle gives you +1/2. And so what do we end up getting? Square root of, oh wait, what am I doing? No, we're talking about angle measures. 60, right? Also known as pi over. Yep. We're done. Right. Let's keep going. Now let's evaluate some tan values. We can easily do A and B. C, we're going to have to use a calculator for that one. So our A, tan of what angle gives you 1? Again, tan is the same as sine of theta divided by cosine of theta. So at what angle is our sine theta and cosine of theta equal? At 45 degrees, right? Sine of 45 is just square root of 2 over 2. Cosine of 45 is square root of 2 over 2. Divide the same number by each other, and we end up getting 1. So our tan inverse 1 is the same as 45 degrees, also known as our pi over 4. What about tan inverse of square root of 3? Tan of what angle gives you square root of 3? I'm going to just set these all equal to theta so that you know, okay, we're solving for angle measures. And so think of, okay, well, sine of theta, sine of what angle gives me square root of 3 over 2, right? Because tan is sine over cosine, and those denominators will cancel out when the denominators are the same. So square root of 3 over 2, that's when sine is 60. So sine of 60 gives us that square root of 3 over 2. Cosine of 60 gives us the 1/2. When we divide these two by each other, denominators cancel out, and we're left with that square root of 3 over 1, which is square root of 3. So our theta here is 60 degrees, also known as pi over what? Keep asking you guys this so that just gets more implanted into your brain. Pi over 3, right? And you'll get more confident and comfortable with this material when you practice more problems on your own too. And then part C, I'll write it out, but we're going to have to use a calculator for this one because it's not a famous angle. So essentially we have tan of what angle gives us 20. And so when you do tan inverse on your calculator, we have second tan inverse, and then 20 degrees. And so we get our theta value to be 87 point, approximately 87.14 degrees. This last one was just to practice using a calculator. Even though you don't get one on the assessments, you end up going into an engineering related field, you're going to be utilizing calculators a lot, and you're not going to be computing a lot by hand. It's good to know the fundamentals. I actually think it's so much more important to know the fundamentals, but knowing how to, especially this day and age, really knowing how to use computers to your advantage, and plug in proper values is key too. Yeah.
So basically, when can be 10 cos we're seeing are negative, we need to find something that when we resolve, the result is positive.
Yeah, because that's the definition of inverse, right? We're reverse engineering the function.
And when the cos we're seeing are negative, and then another number is -2.
Yeah, well, it's not negative if you're referring to this as negative. This
Like for
exponent just reverses it. It's taking the inverse of it.
example, like another one is -2.
You're talking about, yeah, if the solution in there is negative, then you want to apply your knowledge of even and odd functions to see, okay, if it's an even function, then this is the same as just the positive version of it. If it's an odd, then we can take out that negative from the function itself and then just multiply your final solution by a negative value, which is what we did here. Sine is odd, so our solution was pi over 6, but we multiplied it by -1 to get our actual solutions. Yeah. All right. Let's do some more practice. Now, varying it up with sine, cosine, and tangent. So A, right? Sine of what angle gives us 1/2? Yeah, nice. You guys are picking up on it. 30 degrees, also known as pi over. Good. Part B. Sine of what angle gives us negative square root of 2 over 2? Well, sine is an odd function, so this is the same as negative sine inverse of positive square root of 2 over 2. Which means sine of what angle gives us positive square root of 2 over 2? 45 degrees, but then we just multiply it by a negative, and we get -45. In terms of radians, what is this? Negative pi over. Right, let's keep going. Cosine inverse of negative square root of 3 over 2. It's an even function, so this is the same as cosine of inverse of positive square root of 3 over 2, which means cosine of what angle gives you square root of 3 over 2? Cosine of what angle? Yeah, good. Also known as pi over 6. And then last but not least, we have tan inverse of 1. So tan of what angle gives you 1? And we already solved this earlier. 45 degrees, also known as pi over 4. Any questions at all? No. Okay. Let's keep going. Example 6. Solve the triangle below for our angle theta. And so what sides? Think of our acronym SOHCAHTOA. With respect to our theta, what is 9? What type of side? Yeah. What's our 12? Yeah. So what trig function involves our adjacent and our hypotenuse? Yeah. So we can set up cosine of theta is equal to our adjacent over our hypotenuse, which is just 9/12. And we can simplify 9/12, right? Can't we divide the top and bottom by 3? Yeah. So we get cosine of theta is equal to 3/4, which means what's our theta? Now let's apply our inverse function to both sides. So we have cosine of inverse on both sides. We'll cancel out on that left-hand side. So we're left with theta is equal to cosine inverse of 3/4, which on our assessments, I would accept that as full credit, but practicing like on homeworks where you do have the ability to use your calculator, you plug it in and then you get approximately 41.41 degrees and we're done. Okay. Our third objective is finding the exact values of our composite functions with our inverse trig functions. And so this down here is, again, if we're given our inverse function to reverse engineer, we apply sine to our inverse sine, and so on and so forth to get what our x value is. And then if we were looking at it from sine of x perspective, how do we get x all alone? We just apply the inverse of that function, inverse sine, or if we're dealing with cosine, inverse cosine, so on and so forth. All of these we've covered before, what our restricted domains are, and we look at the restricted domains based off of what's inside the parentheses. So sine inverse x has that restricted domain from -1 to 1, but if you look down here, sine of x inside the parentheses has the restricted domain that we chose, our whole -π/2 to π/2. All right, so now let's find each value. And I'll maybe show it to you guys both ways so that you're comfortable with it. First, we'll just do it by the long way of solving it so that we understand. And then we'll apply the rules that we just learned on the previous slide. So what is sine of π/3? What is sine of 60 degrees? Square root of 3 over 2. And then now what's the inverse of that? Sine of what angle gives you square root of 3 over 2? Just π/3, also known as 60 degrees. Which means, right, you take the inverse sine of π/3, and what do you get? You just get π/3. It just cancels out, and our answer is what's inside here. So we could apply the same rule to b, and we end up getting our answer to be what? It just gives us 2π/3.
It's just like say π/something and find which number gives that and which degree give that.
Well, based off of our composite function rules, right? You take the sine of the inverse and you get your value itself, or you take the inverse of the sine and you get your value itself. So it's just, they cancel away. Yeah. What about these? Our answer for A is 2 pi over 3. No. What about B? Yep, done. You guys like these questions, right? Okay. And then evaluating compositions of the form f of g inverse of x. So maybe I'll have a student read this in pink. Feel free to start reading while I just continue to highlight. No one? Ariana.
Evaluate composition of the form f of g to the inverse of x, where f and g are any two of the functions sine, cosine, or tangent, and x is any input in the domain of g.
Inverse, yeah.
We have exact formulas. When we need to use them, we can derive these formulas by using the trigonometric relations between the angles of the sides of a right triangle, together with the use of Pythagoras' relation between the lengths and sides.
Yeah, good. Awesome. So it's just looking at our trigonometric functions from both the inverse and the regular perspective and composing them. So this looks very confusing. I will try my best to really simplify it. The key from this previous slide is we really want to use Pythagoras' relation, aka your knowledge of right triangles. So I'll put that as like a side note. Use your knowledge of right triangles. So we have sine of cosine inverse of 4 over 5. And let's just really zoom in on that cosine inverse of 4 over 5. What is that asking us? Well, if we call this to be our theta, then essentially we're figuring out, okay, cosine of theta must equal 4 over 5. And that tells us, okay, well, if cosine inverse of 4 over 5 is theta, what are we solving for? We want to find sine of theta. And we have cosine of theta. Well, when we're utilizing our SOHCAHTOA acronym, what type of triangles do we use? Right triangles. Good. So let's draw out a nice right triangle. And then let's insert in our theta. We have cosine of theta. Cosine of theta is adjacent over our hypotenuse. Well, our adjacent side is 4. Our hypotenuse is 5. By Pythagorean theorem, our whole a squared plus b squared equals c squared, we get this missing side to be 3, right? 3, 4, 5 triangles. Pythagorean triple. But if you aren't convinced, then you can do it off to the side here. 25 minus 16 gives you 9, and then the square root of 9 gives you that side length of 3. And so that's probably the most important step, because now from here, if we're asked to find our sine of theta, well, what's our sine? What's our so? It's our opposite side over our hypotenuse. What's our opposite side here? 3. What's our hypotenuse? 5. So our answer is just 3/5. Yeah. Lot of maneuvering and manipulation. Now, again, if you had your calculator and you did second cosine, which gives you that cosine inverse of 4 divided by 5, you'll end up getting 36.869897. But then if you take the sine of that answer, you'll end up getting 0.6, which is 3/5 if you convert it to a fraction, 3/5. Again, you won't have your calculators on the exam, which is why it's important for you to manipulate it from that right triangle perspective. Right. Let's do, I believe this is the last example for this section. So our example 10, we have find a simplified expression for cosine in parentheses sine inverse x/3. And we have this restricted domain from -3 up until 3. So this is a little bit more complicated, but the same procedures that we did in example 9 apply. It's just now we have a variable x. So it might look a little confusing, but it's not too bad. Okay, so again, let's really break this problem up. This sine inverse of x/3, we're going to let that be theta, which means eventually we are going to find what our cosine of theta is to get our final result. And so our theta now is equal to sine inverse of x/3. So what does that tell us? That tells us, okay, well, sine of theta gives us x/3. So sine of what angle will give us x/3? When we're dealing with angles and trigonometric functions, it helps us out if we go back to really utilizing our right triangles, and specifically using our acronym of SOHCAHTOA to distinguish the relationship between our angles and our proportionalities of sides. Honing in on our SO, which is our opposite side over our hypotenuse to get our sine of theta. So our opposite side, we have to be, or we've assigned it as our x value, and our hypotenuse we've assigned as what? Or 3, right? So we have x here, and we have 3 here. And then that missing side, our adjacent side, I'll put that in purple. How do we get that? We need to utilize our Pythagorean theorem. So I'm going to zoom in on this. Maybe I'm going to shrink this and then zoom in. So we know Pythagorean theorem, a squared plus b squared equals c squared. Our c is always our hypotenuse, so we're going to replace that with our 3 squared. And then why don't we let this purple side be our a? And then the yellow side can be our b. So we end up with a squared plus x squared equals our 3 squared. And then let's find a. So we'll subtract both sides by x squared. And so we get a squared equals 3 squared is just 9. So we have 9 minus x squared. And then let's take the square root of both sides. So our a value is just simply the square root of 9 minus x squared. You could keep it like that if you wanted to factor out underneath the radical. You can do that as well. Our difference of squares, 3 minus x in parentheses 3 plus x. But you don't have to. The reason why I wrote this second one down is, well, I'll tell you in a moment. You can really see that restriction take place. But so now we know that our a is that whole square root of 9 minus x squared. We're trying to find cosine of theta. Cosine, adjacent over hypotenuse. We just solved for our adjacent side. Square root of 9 minus x squared over our hypotenuse, 3. And this is it. We're done. So why did I write out that whole 3 plus x, 3 minus x? Well, that really shows this restriction, this bound, that x has to be between -3 and 3. Because if it's not, then let's say we plugged in -10 for x, we would end up getting a negative number underneath our square root, which would enter us into the imaginary world. And so this completes our section 8.3. Let me stop recording.